Okay, so welcome to the last section in chapter 4. It's section 4.9. It's called Antiderivatives. So, first thing to do is there's a worksheet available on Canvas. Have it over here, this worksheet on antiderivatives. So I'd like you to do that worksheet and then we'll come back. Okay, so welcome back. We're not going to go over this worksheet. I will post a solution of sorts, or at least what I have put down on Canvas at a later date. But we're going to move on. So the worksheet had you start to think about this idea of doing a derivative in reverse, or what's known as an antiderivative. So we're going to come up with what our formal definition for what an antiderivative is, just to start out. So an antiderivative, and I'll call it capital F of x, for little f of x, is a function such that the derivative of the antiderivative is just little f of x. And that's it. So for example, if you take x squared, well, that's the antiderivative for 2x, because when you take its derivative, you get this equality. Now, the thing is, though, is that if you look at x squared plus 1 and you take its derivative, it's also 2x. And so that's sort of interesting that those are not x squared and x squared plus 1 are not the same function. So, but they're both antiderivatives for 2x. And along that vein, there was a little theorem that we passed over because it wasn't really relevant at the time, back towards the beginning of the chapter. I believe it was during mean value theorem, but basically, using the mean value theorem, you can actually show, and we will not now, but you can show that if f prime of x equals g prime of x, then f of x is equal to g of x plus some number c. And this is a constant. So with that in mind, if we recall our definition of what it means to be an antiderivative, if you have two antiderivatives for the same function, then you know that f prime of x equals f of x equals capital G prime of x. So by this, I'll call it a corollary, because it was a corollary to mean value theorem. We know that capital F of x equals capital G of x plus some constant. I'll put capital C. And so, in this section, we're going to talk about a lot what is known as the most general antiderivative. And what I mean by that is we know that the antiderivative for 2x is x squared is one of the antiderivatives, but the most general one will be x squared plus c. So just always add on plus c. So that's the most general antiderivative. Okay. So let's come up with some rules that we might use. Well, if we have, let's say, x cubed, is there some sort of analogous power rule for antiderivatives? We know there's a power rule for derivatives. That is, for derivatives, it's you multiply first, then you subtract the power. So you multiply, then you subtract exponent. So our first step, if we want to go in the reverse, we need to start with the opposite of doing number 2. So that's add to the exponent. And then divide. So if we want to find the antiderivative of x cubed, that's going to be, well, we add 1, x to the 4th, divide by our new exponent, and then plus c. And so that is one of the rules we can have, the power rule for antiderivatives. And you can do similar thing with addition, works out nice, and subtraction works out nice with antiderivatives, just as it does with derivatives. So we can look at functions like if f of x equals 5x to the 5th minus 3x squared. What is its most general antiderivative? Well, that's going to be 5x to the 6th over 6 minus 3x cubed over 3 plus c, or 6 x to the 6 minus x cubed plus c. So at this point we can look at stuff with polynomials and do this sort of thing. Now we're going to stay away from product rule and quotient rule. If you're interested, take Calc 2 where they'll talk about that sort of thing. But we can look at what are other specific rules we have. Well, we know, let's make a chart. We have derivatives and we have antiderivatives. So let's use our derivative rules to give us antiderivative rules. Well, one of the most straightforward ones is e to the x goes to e to the x. So that's the same for antiderivatives. Now notice, at this point in time, we just have x as the exponent. You cannot do e to the negative x, for example, or e to the 2x yet. Okay? Before, if you had some number, I'll call it a times x, that went to just a. So if we want to go in the reverse, you start with a constant. Now you're not going to 0, you're going to that constant times x. All these are plus c. We had our trig functions. You had sine goes to cosine, and cosine goes to negative sine. So if we want to do that in the reverse, cosine now goes to a positive sign, and sine goes to a negative cosine. And that's just some of the rules that we have at this point in time. You could also talk about other ones like, say, tangent goes to secant squared. So secant squared goes to tangent, and other ones. These are all plus c. And so we can do examples here. So we could start to look at, well, if I take 1 over x, what's the most general antiderivative? Well, that's x to the negative 1. So we can't do our power rule. But what other ones do we have? Well, remember, derivative of natural log is 1 over x. But the derivative of the absolute value, natural log of the absolute value, is also 1 over x. So which one do we choose? Well, this one is the same as this, just with a much larger domain. So in general, we'll say that the antiderivative of this thing is going to be natural log of the absolute value plus c. Okay. And that's just coming from just knowing what natural log of the absolute value its derivative is. Another example is, let's say, sine x plus e to the x. The most general antiderivative would be a negative cosine x plus e to the x plus c. I will take off points if you don't put the plus c. And let's do next. If you have h of x equals e squared, e is Euler's number, e squared is a constant, so its most general antiderivative is not 0, but e squared x plus c. Okay, and so you could keep doing this along this vein, and you'll get practice between the worksheet today and worksheets tomorrow. And so I will continue tomorrow with some more examples, but that is all for today.